So in the last video, we talked about the acid catalyzed synthesis of ethers. Real brief, you have 2 moles of your alcohol. You're using an acid. Notice now I'm showing you HCl, so it really is a proton source. You don't really need just H2SO4 all the time. You could use HCl. You're heating it more than at a temperature higher than 100 to remove that molecule of water. To drive the reaction in the forward direction. Again, protonation, elimination of the conjugate base, and then since this is a primary position, the reaction is going to go through the SN2 reaction mix to give you essentially the propyl version. I'm missing 2 carbons here. For the ether. And we discussed how if you needed an asymmetric ether, how would you go about, what would be the strategy to generate that asymmetric ether. And so here I'm showing you a cyclopentyl methyl ether. And so perhaps you are thinking at this point of time that it could come from a cyclopentanol, right, and a methanol, and that's a possibility. Another possibility would be that you could begin with methanol and add in the cyclopentane ring by some measure. And so just to kind of show you what that might look like, a Williamson ether synthesis essentially starts with an alcohol. And since alcohols themselves are not the best nucleophiles, we generate a good nucleophile out of it, because what it is at the end of the day is a substitution reaction. So you treat it with a strong base, such as a super base, like sodium hydride, for instance, and that will generate the alkoxide. The alkoxide we know is a good base. So now if you treat that with an alkyl halide, it's going to kick off the halogen atom and it's going to form the ether. So let's say you started with R prime OH, that will generate an R prime O negative and will go through the substitution reaction. So Williamson ether synthesis is nothing but based on a SN2 reaction mechanism. Now, it's important to recognize and take one step at a time, that if I had a simple ether, like perhaps I had a ethyl group on one side and I had a propyl group on the other, it really doesn't matter how you would cleave it. You could totally start with propanol, generate the propoxide, and treat it with ethyl iodide. On the other hand, you could also break it over here, start with your ethanol, generate the alkoxide, and treat it with propyl iodide. So your 2 possibilities that I just mentioned are that you start with ethanol, you treat it with maybe sodium hydride, that generates the sodium ethoxide, treatment with iodopropane is going to give you your molecule. The other possibility is that you are starting with propanol. Again, the whole 9 yards. Sodium hydride is what you're treating it with. Sodium propoxide is what you get. You're treating it with iodoethane, and you get your molecule. So when you have simple molecule, primary carbon atoms on each side, it doesn't matter which way you go. You can just simply cleave it on one of the sides and you're good to go. The problem arises when one of the sides actually contains a secondary carbon atom. And when that is the case scenario, you would want to start with the alcohol of the secondary position. That means you would want to put the oxygen already built into the alcohol. And for that reason, you would want to, for a molecule such as the one that I'm showing you here, the cyclopentyl methyl ether, you would want to start with cyclopentanol treat that with sodium hydride so that you end up with your cyclopentoxide ion, and then let that go through the SN2 reaction with methyl iodide, THF as the solvent, to get your final molecule. Let's take a look what will happen if you don't do that. So so my target molecule is this, and right now what we did was we started with the cyclopentanol. We treated it with sodium hydride. That gave us sodium cyclopentoxide. I threw in my methyl iodide. Attack takes place at the methyl position. Whoa. And you end up with the molecule that you desire. What would have happened if you would have gone another way? That means if you would have broken the bond in red. Okay, so that means that you would have to start with methanol. You would treat it with sodium hydride. Let's go ahead and write down our methoxide. That's not too hard. You guys are used to doing that now based on chapter 17. We know that hydride is a super base that's going to pick up that proton from the amphoteric alcohol. Methoxide will be generated. Hydrogen gas will be generated as well. And now I have my sodium methoxide, and I'm going to throw in, because I'm supposed to put in an alkyl halide, I'm going to put maybe bromocyclopentane. Okay. Now, the nature of this alkyl halide is that it is secondary. And whenever you have secondary or tertiary, for that matter, alkyl halides, then the incoming nucleophile can also serve as a base, because these are susceptible to going through an elimination, an E2 elimination. They love to do that. What does that mean? That means that the beta positions are going to receive that negative charge, electrons will move, bromine will leave, and your primary product will be an elimination, cyclopentene, rather than the substitution reaction. Okay, and that is the reason that you would want to always start with the oxygen already as a part of your alcohol. So the alcohol that you begin with always has got to be with the secondary position. So here I'm showing you exactly what we talked about. If you have cyclohexanol treatment with sodium hydride, THF as your solvent, you get sodium cyclohexoxide. And now when we treat it with ethyl iodide, your reaction will take place at the primary position. You end up getting your desired molecule. Your Williamson ether synthesis is ready to roll. Your iodine, which was lost as iodide, is going to join hands with the sodium, so you're going to get the NaI as your product. Now I'm showing you here, that the I minus, but you don't have to really show this part. That's implicit. That's considered that when you have a positive and the other is negative, that is going to pan out. You don't have to show that as a part of the mechanism. So just show how the hydride picks up the proton, electrons go on top of that, possibly show that as two separate steps, just the way I showed in the previous slide. So go ahead and show that as the hexoxide, which is then going to react with the primary position and show the loss of the iodide. Okay. All right, so let's see if we can write out the products for this reaction based on what we heard. So sounds like when my oxygen is next to a secondary position, ta-da, that substitution will take place and you would end up getting a SN2 reaction. On the other hand, if that were to happen for a secondary halide, then elimination will take place and you would end up getting cyclopentene. Okay, let's see if you are able to apply what you have heard on some molecules. So pause me here. Step number 1 should be to draw it out. Step number 2 should be think. Step number 3 should be come up with a Williamson ether synthesis. That means identify which alcohol, which super base, which alkyl halide should be put together in a sequential 2-step synthesis. So go ahead, pause me, and then check your answer. Notice in this case you have a methyl on one side and you have a propyl on the other side. It doesn't matter whether you break A or whether you break B. Both of them are going to be pretty good in the reaction mix. So you could begin with CH3OH, treat that with sodium hydride. That's going to give you CH3O negative Na plus. And you're going to, when you give it a Br plus CH3O negative Na plus, that negative is going to attack, Br is going to leave. You would end up with the molecule that you desire. Another way to do this would be that you have propanol, you treat it with sodium hydride. That gives you sodium propoxide. And now I'm going to add the methyl. Attack takes place. Bromine leaves. There you go. You have your product. So one way or another, you have your product by cleaving on each side. The next one is anisole. Here, you either could start with methanol or you could start with phenol. So your choices are that you take phenol, maybe you treat it with sodium hydroxide, that forms the phenoxide, and then we are going to treat it with the methyl bromide. Reaction will take place, you get your product. Another possibility, I'm going to just put an asterisk there. Another possibility would be that you start with methanol, treat it with sodium hydride, that's your bromobenzene. We want to attack here and we want the bromine to leave and then get the product. I want you to pause me and evaluate whether you like the blue or the red. Which group of reactants do you prefer for this reaction to go through using Williamson ether synthesis in synthesizing anisole? If you chose blue, kudos to you. That kind of rhymed. Well, think about it. You have phenol and we are treating that with sodium hydroxide, which is actually not a problem because methanol with sodium hydride, but what we are trying to get to is that our phenoxide that we have is going to be stable, right? There's more likelihood that that will happen. But even bigger than that is the second step. So in the blue reaction, my phenoxide is going to attack at the methyl, bromine is going to leave. On the other hand, in the red reaction, I'm predicting that my methoxide is going to attack at an SN2 center of the benzene. A substitution reaction, I told you guys in Organic 1 that an SN2 reaction does not take place at an sp2 hybridized carbon center. In this case, that happens to be the benzene ring. Recall what we know about the bromobenzene. You have the lone pair of electrons, right? And we can write down resonance structures where this carbon-bromine bond will not just contain, it will not just be a single bond, but rather it will be a bond with a partial pi character. So if you were to draw out all the resonance structures, not only would you get the two ortho positions and the para position, not only would you get a higher electron density at those three positions, those three locations, when you actually draw out your overall structure, you would see that the benzene ring contains the electrons spread over the entire ring, as well as the carbon bromine bond. So at any given point of time, we are not suggesting, we are not saying that it is going to be a single bond. And what do you think? What do you know? Is it hard or is it easy to break that carbon bromine bond? Yeah, it's going to be harder because essentially that will be stronger bond as compared to the single bond that you have in case of the methyl and the bromine. Does that make sense? What I want you to do is take a moment. I kind of gave you a mini case, and this is the way how you might see some of the questions structured. So I will give you, two possibilities, and you will have to pick which one of them is a better deal, but you will have to reason it out. So that could be in that reasoning section of your test. It could also be in the take-home quiz. Take a moment to write it down for yourself as to why we think what we think, and then join me back. All right, let's take a look at this reaction over here. I have been given an alkyl halide, I have been given an alkoxide, so they must have synthesized this alkoxide with the sec-butanol, right? And they would have subjected that to treatment with sodium hydride, being an alcohol. So this is a secondary position, and so is the secondary position on the bromocyclohexane. What do you think would the product be in this case? Yeah, I mean, in this case, you are going to end up with a mixture of products because you have your bromine, and that's a good leaving group. We talked about this, that if you have secondary or tertiary alkyl halides under these conditions, they will be susceptible to elimination. So you are going to eliminate and get cyclohexene because that is where your beta hydrogens are. So this is beta, this is alpha. So your base will pick up, and depending on the temperature of the reaction, which they have not specified, this might give you tad bit, just a little bit of your substitution reaction as well, but so slow and so little that it would be a little bit impractical. So the question then becomes, well, if I want to synthesize this type of a molecule, so on the cyclohexane, I have the sec-butyl group across the oxygen. So I have an ether, and both the positions are secondary. Is there another alternative that we could perhaps consider? So we talked about the acid catalyzed symmetric ether synthesis. We also talked about the Williamson ether synthesis. Is there another reaction that we could perhaps think about which would, could, should give us the desired product? Let's take at another one. And what comes to mind is the alkoxymercuration of alkenes. So recall what we did. We talked about oxymercuration, demercuration in organic one. And if you've forgotten, I'm going to very quickly remind you what that reaction was. That reaction essentially was that you could start with maybe methyl cyclohexene and you treat it with a mercury salt, typically mercury acetate, but you could totally use triflate, chloride, something like that, with water. It first is going to form the three-membered mercury ring, right? And then the water is going to ring open from the back side, so it will be like a trans addition, if you will, and that will give you mercury still connected. You first will get the OH2, of course, and the acetate that was lost in the very first step. Let's just show that out as well. That's going to pick up that proton. Electrons are going to go on top of oxygen, and so you would end up getting HGOAC OH. And now in order to break the carbon-mercury bond, you're going to just reduce that with sodium borohydride, THF, and that gives you your HOH following the Markovnikov's rule. That's your product. And it was argued, well, if we use HOH, we get an alcohol at the end of the day. What if we use an ROH? Going through the process, would I be able to get an OR? That means if I need an ether that looks like, that was our ether, right? I could start with my alkene, and my alkene in question would be cyclohexene, because that's where the reaction will take place. But I will have to ring open with this entire, your sec-butanol is what I would have to ring open with. So the way the reaction will pan out would be that you would treat it with mercury acetate and you would ring open with sec-butyl alcohol. And so as a first step, the oxymercuration, I'm going to write down the OAC so that I can show that that lost. And you would get the 8GOAC, positive charge in between. It's basically shared. And then we have our alcohol that's going to attack. It's going to come from the back. The ACO negative, which is the acetate, that's going to pull the proton off, and that would give us our ether. However, we still have to go ahead and reduce our mercury acetate. So as a second step, we will have to treat it with sodium borohydride, THF, and that will give us the desired product. So pretty simple reaction, something that you have done before, but this was a modified alkoxymercuration of alkenes, which allowed sort of like a little bit of a greater diversity of ethers that may be able to built in, because we were kind of taking away that elimination, which was a problem point in Williamson ether synthesis. So if somebody says, well, what was the problem with Williamson ether synthesis? The problem was that you're restricted to starting with the secondary position always being held by the alcohol. That's your beginning point. And if you happen to have a secondary or tertiary position on both sides, then there's no way you can use Williamson ether synthesis. You will have to think about a different method. And this was a method that was suggested and has been used towards that goal, towards that aim. So over here, I'm showing you the synthesis of methoxy, 1-methoxy, 1-phenylethane. Maybe it looks familiar to some of you. We are starting with styrene as our starting material with our mercury triflate. Notice the difference between triflate coming from triflic acid and mercury acetate coming from acetic acid is just that the 3 hydrogens have been replaced by the 3 fluorines. So that's the only difference between the two. And instead of course, the big sec-butanol that I had in the previous example, now I have the methanol as my alcohol, as my nucleophile. And the reason for that is, of course, because the ether that I see, the ether has got to come, it is a methyl ether. So methanol would be my alcohol of choice. And as I go through the reaction mechanism, I would have the 2 methoxy group and the mercury triflate pointing in opposite directions, and upon treatment with sodium borohydride and THF as the solvent, I would be able to get my desired product. Check out the yield, 97%. That's a really good yield for this reaction. So pretty good standard method, robust method to get a diverse variety of ethers that you may need. So I have ethyl phenyl ether here, and we have talked about two different methods. Hopefully you can see how you can remove the proton of the phenol using sodium hydroxide, treat it with your bromoethane, and that gives you the ethyl phenyl ether. Another way to think about it would be if you start with your ethene, carry out the treatment with mercury acetate or mercury triflate, and ring open that with phenol. And that would give you your phenol with your mercury acetate still stuck on it. And when you treat it with sodium borohydride, THF, you end up getting your desired molecule. So two completely different methods to get asymmetric ether. That's what we are focusing on right now. All right, so let's talk about the chemical properties. The beauty of this chapter is that there are very few chemical properties of ethers. For students, however, that becomes a challenge because there's not much tangibility of it. When we talked about alcohols, the challenge was that the volume was too much. There were too many reactions, right? Sometimes there was an OH bond that was breaking. Sometimes there was a CO bond that was breaking. In case of ethers, there's very little because these are generally unreactive. And while it is a very simple chapter, sometimes when something is too simple, we don't know to what extent we should emphasize and in what direction. So as we go, I'm going to write down the appropriate mechanism for each of those, as I have been doing in the past, and it is your responsibility to please make it a point that you are able to draw out each of those. So like I said, ethers are generally unreactive, and the only time they will react would be if you treat them with strong acids, and I'm not talking about something like HCl or so, but really strong HBrHI, hydroiodic acid or hydrobromic acid, and you're doing that at elevated temperatures. That means typically you would be setting this reaction at reflux. So that's an important point. Depending on the nature of the starting material, the kind of ether that you have, the reaction could go through a potentially SN1 reaction or SN2 reaction. The general scheme of things is that you should check if either side of the ether contains a tertiary position. If there is a tertiary position, then a very stable tertiary carbocation can be generated, and the SN1 reactions will become more facile, more feasible. On the other hand, if both the sides are either primary or primary and secondary, then it would be facilitated via an SN2 reactions. So let's see if we can actually process map this idea together. What I'm saying is that what you are doing is that you have maybe like an asymmetric ether of this kind, and you're subjecting that to treatment with HX, and you're heating it, you're setting up to reflux. One of these three would be written, and your product is going to be either ROH or R prime OH, right? And the other one is going to become the RX. So the first step is of course going to be H, helping out with the protonation. So you have the oxonium ion that gets generated, and now the molecule has a choice. The X minus can attack from R prime side, or it might attack from the X side. And how do we decide which side does it attack from? In order to tell that, this is what we are going to check. We are going to ask the question, does either of the sides contain a tertiary carbon? If the answer to this is yes, then you would want to attack, you would want to form the carbocation first. So form the tertiary carbocation and let X minus attack the tertiary position. If the answer to this is no, then you're going to just follow SN2. This is of course SN1. You would just follow SN2 if the answer is no, and you would attack from least substituted side. Okay, let's see if we can apply this process map to the whole idea, to the next 8 or 9 slides. Okay, so here I have ethyl phenyl ether. I'm treating that with HBr. Notice they're saying HBr H2O. You don't really add H2O, but HBr is just sold as a 48% solution in water. So that is what you get essentially. The first step, of course, will be the protonation. So you're going to go ahead, carry out your protonation. That will look like protonated, yep, this. And now you have a choice whether your incoming Br minus comes in from the least substituted side or whether it comes from this end. Which direction should you put the bromine in? So pause me, come up with an answer why you would say what you would say, and then see if it matches. Basically, like I was telling you, you have to check whether any of the two sides is tertiary or not. So on the right hand side you see a primary carbon. It's connected to only one other carbon, and on the other side you see an aryl position. So neither of them are tertiary locations, and for that matter you're going to simply use your least substituted side as the side from which the reaction will take place. And so no blue, you're going to follow the red, and the product will be bromoethane and phenol. So as the bromine attacks, phenol will leave, and you are going to get your phenol and bromoethane as your two products. Sound good? All right, let's go forward. Over here, I have 2-ethoxypropanoic acid. We have HI, and we are treating this. We are heating it, of course. So as a first step, hopefully you can see that all you got to do is protonate your oxygen, and that's going to give you the protonated molecule. So again, we have to ask the question whether we have something that's tertiary or not. So let's check that out. This carbon is a primary position. This carbon is a secondary position. That means this is susceptible to a SN2. That means you must attack from the least substituted side. So your incoming iodine is going to come from the least substituted side. You would end up getting lactic acid and iodoethane. Those will be your two products. Again, to reiterate, our reaction is going to go through the first protonation, followed by attack of the nucleophile from the least hindered side, following the SN2 reaction mechanism to give the alcohol and the alkyl halide. And those are the two products that you would see for the acidic cleavage. Note that the acid that you would be using is going to be nothing other than HBr and HI. Those are among the strongest acids known. And you will have to reflux this, so it will be elevated temperatures of like 100 degrees or beyond. All right, so here I have 3 reactions. I am going to put down the answers, but you should really pause me if you want to learn how this pans out. And so pause me and then match your answer whether or not it matches with what we have here. I always like to write down the mechanism, especially when we are starting out. So I'm going to go ahead and show you that mechanism. But if it's a fill in the blank type of a question, there's no reason to put down the mechanism. This is just a thought process. So what was the question that we wanted to ask? Yeah, we have to look for the tertiary center. Is there a tertiary center? Yeah, there is. And on this side, no. So since there is, we are going to break this bond. So we are going to go ahead and let the propanol leave. And that will also generate the T-butyl carbocation, which is where the bromine is going to go in and attack and give you the alkyl halide. On the other hand, if you had the second one, That's where you have your again, the protonation will take place. This side it does have a tertiary carbocation. The other is just a methyl. Again, following our process map, we must break the bond following the SN1. That means the methanol will go away. And we will get a super stable carbocation. And you might be wondering, why do we have this difference? Well, whenever we have the opportunity to form these tertiary carbocations, we would grab that opportunity, because the molecule is going to essentially get, you can consider that the energy tax, right? So it is extremely stable. And so why would the molecule not want to go in that direction? And so this, imagine this is a tertiary location and it is a benzylic position. That's like two things, two aims accomplished. The molecule is like really happy. This intermediate is extremely happy. And now when you have your Br minus, that's going to attack, and you're going to end up with your benzene ring, two methyls, and the bromine in place. Let's go ahead and take a look at the last one. Hopefully you can. Maybe you're ahead of me. And go ahead, show your protonation. And now you have a secondary and a primary. So which one would it be? SN2. Good job. And so you must use the least substituted side. You got it. And that's it. Nothing more than that. Okay, the other reaction that comes to mind, which is possible in some ethers, and these are very specific ethers, these are called as aryl ethers, is the Claisen rearrangement. So in the next two slides, I am going to talk about the Claisen rearrangement. Like I said, it is specific to aryl ethers. Anybody remember what is the meaning of aryl? What's aryl? Aryl means that from the ether you will have 3 carbons coming out, and the double bond will be from the oxygen, it will be at one position over. So if it would have been a vinyl ether, we would have said that oxygen connected to the double bond, right? That would have been vinyl. This is allyl. That means it's 1 carbon over. The other side is aryl. That means it would be connected to some kind of a benzene ring. It could be a substituted benzene, something like that. Now, first things first, how do you synthesize these? Pretty easy. Usual Williamson ether is a good strategy. Start with phenol, treat it with sodium hydroxide or sodium hydride. That will give you your sodium phenoxide. So you could use the sodium hydride. You could also use the sodium hydroxide because it's a phenol. That reaction will work well. And then we are going to treat it with your allyl halide. Allyl halide will be something like this. And so the negative charge is going to attack, Br is going to leave, and there you go. You got your allyl phenyl ether. Now, we are going to carry out our Claisen rearrangement. That basically means we are going to heat it. And that will lead to a rearrangement to form orthoallyl phenol. Look at that. We are starting with an ether, and we are ending with a phenol. How is that going to, or what is going to happen in that case? Let's first, for the sake of argument, just kind of number some atoms. So there is a group of 3 atoms here, and there is a group of 3 atoms over here. 1, 2, and 3. What's going to happen is that it will be completely synchronous, that the pi bond from the benzene ring is going to, from the 2 and 3 bond, is going to go between 3 and 1 prime. The bond between 1 and 2 is going to shift between 2 and 3 prime. And the bond between 3 and 1 is going to move between 1 and 2. Okay? If you want, we can write it a little bit bigger so you can see what's going on. So again, notice what we have. We have a group of 3 atoms, 1, 2, and 3. And we have the other group. I'm going to call it 1 prime, 2 prime, 3 prime. Perhaps I'm going to even color code them a bit to get your attention. And my purpose is going to be that I have to shift the bond between 2 and 3. That's going to come in between 3 and 1. The bond between 1 and 2 is going to go between 2 prime and 3 prime, and the bond between 3 and 1 is going to break. So that's how we are breaking the bond. Okay? Now you might say, why would you want to do that? You would want to do that because your transition state that gets generated, which is a high energy intermediate, is actually a 6-membered ring. Always happy to form, right? So this will happen. This is not like a no-go. This will happen. Of course, it will require a greater amount of energy for the reaction to take place. But notice what will happen when this bond breaks. I'm going to just highlight which ones are the ones that will break. This bond will break, and this bond will break. And I'm going to maybe put down the ones that will be made. This will be made, this will be made, and this will be made. So there are 3 alternative bonds that are broken and 3 alternative red ones that are made. Your product will look like a ketone. And of course, you have the double bond that has been used up. You made a new bond here. You made a new bond here. And you made a new bond here. Okay? You have a ketone as an intermediate. And when I say ketone, what should also come to your mind? Yeah, it's enol version. So you have here the ketone, which is present in its non-aromatic structure, CH2, CH, and the double bond. What can happen is that you can carry out a rearrangement. 1, 2, and 3. These electrons will pick up the proton and the CH bond will collapse. So that shift will take place and you will end up getting your phenol, and the ortho position will hold the allyl group. Since we had a group of 3 atoms on each side, which kind of went through this concerted, synchronous bond breaking, bond cleavage, and bond making, that essentially is also referred to as a 3,3 sigmatropic rearrangement. So it is a rearrangement reaction, perfectly orchestrated, where you are going to have a stable 6-membered transition state, generates a ketone. But notice that this intermediate is not aromatic. It's non-aromatic. So it would want to regain its aromaticity like ASAP, and hence it will form the enol, which by the way is the aromatic phenol, and give you the corresponding product. Let's see if we